Okay, so let's look at how to find our empirical formula given masses, not mass percents, just absolute masses. And the process is exactly the same way. I'll be very honest, because what was the first thing that we did in our previous example? We assumed that the total mass was 100, and so we just changed those percentages into masses. But I wanted to use this example when the subscripts aren't exactly perfect. You should find that in most cases, except possibly when you're doing things experimentally, most of the examples or questions are going to be given as part of homework, sapling, now you try it, whatever. The numbers should come out pretty well. So if your numbers look a little screwy, check to see if you did something wrong, or see if there's a way to get them to be whole numbers. Look for common decimals. So let's suppose I have a compound. Let's start this again. Here. So a sample of a compound is found to contain 6.00 grams of carbon, comma, 0.448 grams of hydrogen, and 3.55 grams of oxygen. Determine the empirical formula for the compound. Okay, so again, first thing, this time we actually already have our masses, so determine moles of each element. For carbon, I'm given 6.00 grams of carbon, and I need to find moles. So to go from grams to moles, you use that molar mass, and 1 mole of carbon is 12.01 grams. And Then I need to do 0.448 grams of hydrogen, and 1 mole of hydrogen is 1.01 grams. Finally, oxygen, and we had 3.55 grams of oxygen and 1 mole of oxygen is 16.00 grams. All right, so I do the calculation here, and I have 0.4996, and here I have 0.444, and here rounded it becomes 0.222 moles of O, moles of H, moles of C. So the next step is to go from the moles and to find the whole number ratios. So I've got carbon at 0.4996. I have hydrogen at 0.444, and I have oxygen at 0.222. Once again, divide by the smallest, 0.222, 222, 0.222. And when I do this, I end up with carbon 2.25, hydrogen 2, oxygen 1. This is too far away for rounding. But I do know 0.25 is the same as 1/4. What this means I'm going to do is multiply each subscript by 4. The other ones are easy. 2.25 times 4 is 9. So I have C9 H8 O4. All right. The pieces that we've touched on so far. We've talked about finding the molar mass. Two. We did mass to moles. Convert moles to mass. In the empirical formula calculations, that was simply taking mass and going to moles. That's all it was. And then that mole ratio. We've even talked a bit about going from, well, I wouldn't say we've done a bit. Now we've also done empirical formula. And molecular formula. And stuck in here with the empirical formula, we did touch on percent composition. None of that has anything to do with chemical reactions at all. At all. This grouping, especially 1, 2, and 3, forms the basis for stoichiometry. Last lab, we actually used a piece that is very vital in understanding chemical reactions and approaches to chemical reactions. And that was looking at the relationship between volume and concentration to get moles. So the last section in this chapter talks about molarity. And molarity is moles of solute per liter of solution. Molarity is a concentration. So how much solute has been dissolved by the solvent? Concentration. Solute. Is there in the lower amount. Solvent is present and larger amount. Now, we really only need to worry about larger amount, lower amount if we're trying to mix two liquids together. If we're talking about a solid getting dissolved by a liquid, the solvent is what does the is what does the dissolving. Most of the solutions we will be talking about, we will have water is going to be our typical solvent. And since water is our typical solvent, we end up calling these aqueous, A-Q-U-E-O-U-S, aqueous solutions. And that gets abbreviated AQ. Molarity allows a chemist to measure a volume So we can measure the volume of a solution and know the number of solute particles. And again, why is that important? Well, the way we understand how chemical reactions happen, solute particles react, or sorry, reacting particles have to hit each other. So if we want to play, for example, with how fast something reacts, and we can up the number of solute particles, well, we should then be able to up the rate of the reaction. Okay. So what is the molarity of a saltwater solution in 0.250 moles of salt are dissolved to make 100.00 milliliters of solution? Question mark. Molarity is moles solute liter solution. Coming up and taking a peek at this question, what is the molarity of a solution if 0.250 moles of salt are dissolved to make 100 milliliters of solution? One of the things that you will want to become adept at doing is a very rapid conversion between liters and milliliters and back. 100.00 milliliters. Well, 1 liter is 1,000 milliliters. 0.10000. 10000 liters. And then 0.250 moles. .250. Let me write that answer down a line here. 2.50, capital M. So capital M is our molarity. So that's one type of question that could be involved in playing with this idea of solutions. Another question has to do with making a solution. What is the molarity of a solution formed when 5.8 grams of NaCl, 58.44 grams/mole is dissolved to make 0.250 liters of solution. And I will admit, I quite often abbreviate solution SOLN. I'm going to come back to my formula. Molarity equals mole solute. And in this case, my solute I know is NaCl over liters of solution. Well, in this case, I'm not playing with 1 liter of solution. I'm playing with 0.250 liters of solution. My question then has to be, if I'm after the molarity, my question then has to be, what goes in the green box? What goes in the moles? So someplace else, I'll do this calculation. How many moles of NaCl equals what? What information do I have about the NaCl? There's my solute. There's my solution. The part that I have about the NaCl is that there's 5.8 grams of NaCl. I know that I have grams. There's 58.44 grams for every 1 mole of NaCl. And yes, I'm trying to pick numbers that are pretty straightforward. So 5.8 divided by 58.44 be pretty close to 0.1. So my answer is 0.09925. And then squeeze mole. NaCl. And so now I can take that answer, 0.09925, and I can do the division now, 0.25. Final answer, 0.3969884. Well, I carried too many significant figures with my mole of NaCl. It should have been rounded to 2 sig figs. But remember, I'm going to carry around more than I need to and dump it at the last moment. So rounding for sig figs, 0.40 molar, and then we put down what the solute is. So 0.40 molar sodium chloride. So here are two examples of determining molarity. Sample 1, I give you moles, I give you the volume, give me molarity. Sample 2, I give you a mass, I give you the volume of your solution, find me molarity. So those first two examples we could put as determining molarity. Now, those next examples, so examples of using molarity. One piece I would like to instill in you, working with molarity, working with molar masses, working with densities, they are all conversion factors. Every single one of them is a conversion factor. Molarity is no different. Again, because between something that we can measure, volume, and something that tells us how many pieces or parts, moles. So molarity is a conversion factor. For example, I have that 0.40 molar NaCl solution. Right? A better way to think about this, instead of just leaving it as capital M, 1 liter of the solution is equivalent to 0.40 moles of NaCl. So once again, this conversion factor goes between something I can measure, a volume, and how many pieces, how many parts do I have? Just as an aside, molar mass is a conversion factor. So that 58.44 grams per mole. 58.44 grams, something I can measure, is equivalent to 1 mole of NaCl. And you come across these many times. Many times. And if you can, try to keep that molar mass is a conversion, molarity is a conversion. And sometimes it really does help to establish these as written out more like conversion factors than have it shrunk inside the molarity. Students seem to really struggle with that capital M being two separate pieces, okay, being the conversion factor between two things. So let's do some examples using molarity. So how many grams actually, let's do this. Let's take it half a step at a time. How many moles of NaCl are in 125.0 milliliters of a 3.0 molar NaCl solution? Question mark. Okay, so let's see what we got here. How many moles of NaCl are in 1.250 milliliters? .0 molar NaCl solution. I see this, the first thing that I think is, once again, 3.0 capital M there's 3.0 moles NaCl in every 1 liter of solution. No, that 3.0 molar NaCl I like to interpret it written out that way, because now I see that it's a conversion factor between the two pieces, between moles and volume. If you feel a little sneaky, I don't know how sneaky this is, you could write this as 3.0 moles NaCl. And then what does 1 liter equal? 1 liter is 1,000 milliliters. So if you'd like, you can go ahead and use it that way. Got no problem with it. If you feel more comfortable doing the conversion elsewhere, that's fine. I'm going to show it with the conversion. All right, so let's see here. How many moles? Question mark moles. NaCl. Never start your calculation with a conversion factor. That means that I have to start my calculation with this with 125.0 milliliters. I know molarity is in terms of liters. So the first thing that I'm going to do is 1 liter is 1,000 milliliters. Now I can use my molarity, and I have 3.0 mole NaCl per liter. So now just a little bit of number crunching. Come on, let's see, 0.125 times 3. So I end up with 0.375, and that gets changed to 0.38 mole NaCl. Molarity is an experimental. It is experimental. Now, of course, this is nice. This is really what we did with the determining the mole ratio. What volume did you use? Oh, we used what? 30, 25. I'll take that back. We use 60, right? We use 55, 50, 45, 40, 35, 30. We walked our way through the various volumes. But how did you find moles? Well, you took the volume that you used, converted it, took the volume that you used, converted it to liters, and then used the molarity. How many grams of NaCl are needed to make 250 milliliters of a 1.50 molar NaCl solution? Question mark. And then you may see me be nice and say something like the 58.44 grams/mole NaCl. How many grams NaCl? Are needed to make 250 milliliters of a 1.50 molar solution. And then I'm guessing this piece might be important as well since I added it in. Okay. I'll give you a couple of hints. I would say probably 9 times out of 10, if not more. If you see grams within a question, you will need a molar mass. Let's put this in red. So the term grams or just mass means that you will probably need molar mass. So just a little heads up. Okay, now let's break it down. Break down what we got. We have, I've got how many grams NaCl. And then I have something else that is 250.00 milliliters. I'm getting rid of all the words. I'm just getting rid of all the words. And let's see, what else do I have? I've got 1.50 M NaCl. And the last piece, I have 58.44 grams/mole NaCl. In my mind, this makes sense. And I apologize. I apologize if all of a sudden I took you off the rails. Okay. Essentially, all I did was pick up the pieces that I've highlighted and move them down into a new work area. The two pieces in particular I want you to pay attention to are those two. Those are unit conversions. 1.50 moles NaCl is 1 liter of solution. there's 58.44 grams of NaCl for every 1 mole of NaCl. Those are unit conversions. Don't start there. If I'm not starting with my unit conversions, there's my starting point. I'm after grams, how many grams of NaCl equals 250.00 milliliters. Well, I know that I have 1 liter for every 1,000 milliliters. So the milliliters will cancel. And I know that there's 1.50 moles of NaCl in 1 liter of my solution. And the last piece that I have is that for every 1 mole of NaCl, it's 58.44 grams. And let's see, going through and double checking. Oh, I'll use gray, milliliters, milliliters, liters, liters, moles, moles. Yep, all my units cancel. So now I can go ahead and plug and chug 250 divided by 1,000 times 1.5 times 58.44. Boom. I have as my answer 21.915. And then rounding to sig figs, that would be 21.9 grams of NaCl. There are certainly other types of questions that could be asked. If you notice the question that we just did, it was how many grams of a particular solid are needed to make this volume. Well, we could also ask a question along the lines of what volume in liters is needed will contain, let's see, what volume in liters of a 5.62 molar NaCl solution will contain let's see, I will go fine. We'll go 102 grams of NaCl, question mark. All right, so what volume in liters of a 5.62 molar solution will contain 102, oops, will contain 102 grams of NaCl. Once again, grams of NaCl molar mass. One mole NaCl is still 58.44 grams. The other piece that just absolutely screams to me is at 5.62 molar. That means there's 5.62 moles of NaCl for every 1 liter of solution. Starting point. How many liters equals 102 grams NaCl? Want to get rid of grams NaCl. And for every 1 mole of sodium chloride, that's 58.44 grams. Now I need to go to liters. I have moles of NaCl, so I want to get rid of moles of NaCl. And I want to go to liters. Well, according to the question, there's 5.62 moles of NaCl for every 1 liter of solution. So 102 divide by 58.44 and then divide by 5.62 will give me 0.311 liters of solution. The last piece in this chapter that I'm going to talk about is what's called dilution. Dilution occurs when you take a small volume of a high concentrated solution and add solvent to get lower concentration. The thing to remember when we do dilutions the number of moles remains constant. Suppose I have a pond, and in my pond I have some fish, E-I-E-I-O. So I've got some fish in this pond. There's a certain concentration, correct? Please say yes. Now, what happens if I take this amount of material and instead of leaving it in the same size, I put into a much bigger puddle? I have the same number of fish. I don't even want to count. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay. So I have the same number of particles. I just have it in a larger volume. So let's just suppose I have a certain concentration, and I'm going to take a certain amount of it, and then I'm going to dilute it. Okay, so let's say I take, I don't know, 100 milliliters of my solution. Okay, so I'm going to take 100 milliliters of a solution that is 26. Come here. Stop it. 26 fish. Oh, I don't like this. Yeah, we'll go with 26 fish per liter. There we go. Okay, so now, no, I don't like that. Sorry. This is when you're trying to work through a new analogy and it's just not clicking for you. Not clicking for you. Okay, so let's see. We can do it this way. Okay. I'm going to have 1 liter of 26 fish per liter. Okay. And I'm going to take that 1 liter and put it into 2 liters. Okay, make 2 liters of solution. What is the new concentration? Well, here I have 26 fish for every 1 liter, right? Here, okay, when I put them in the bigger container, how many fish did I put in? I made that point of counting 26 dots. I got 26 fish. But those 26 fish are no longer in 1 liter. They're in 2 liters. That means my new concentration is 13 fish per liter. If you double the volume, the concentration is cut in half. Okay. So the two things are inversely proportional. If we go back and look at it purely as a mathematical thing, molarity moles per liter. What happens if I take volume in liters and multiply by something with the units of moles per liter? Just unit-wise. Gives me moles. However many fish that I put into that new tank, that can't change. When we do a dilution, we have what's called the concentrated or the stock solution. The stock solution is the one that we have in the stockroom. It is the one that we start with. Oftentimes you will see this abbreviation as M1 V1 equals M2 V2, or there are a number of things that we can use. Again, if I take a volume in liters, so if I take liters, and multiply by molarity. That will give me moles. The number of moles that I take out of my stock solution. So if I have some particular volume of my, I don't know, stock solution. So S means stock. So if I take some volume of my stock solution and I multiply it by the concentration. So if I stop it, so close. And I multiply it by the molarity of that stock solution. That equals moles. So I'm going to take a small amount of something that's highly concentrated. Well, that number of moles, when I put it into my new container, I will have a dilute concentration. And I will have a dilute volume. So D equals dilute. And I usually have these flipped. It really doesn't matter the order in which you multiply. Just to give you a little insight, the lab that we did where we were using 1 molar acid and 1 molar sodium hydroxide, I'll tell you right now that we were running out of both of those in the 1 molar concentration. What we had in the back, however, was 6 molar. Well, the bottle that I had was 500 milliliters. After lab on Tuesday, this is what I did. I needed more. Whoop. 1.0 molar NaOH. I had 6.0 molar NaOH. How many liters? Well, actually, I can do it in milliliters. How many milliliters of the concentrated base so how much of that concentrated solution did I need? To make 500 milliliters of 1.0 molar NaOH. Question. As long as both volumes are in the same unit, I can leave them. I don't have to change out of that unit, which is really, really nice. All right, so let's see here. I have on one side, let's do my concentrated side. And then I will have my dilute side. For my concentrated side, I know that I have 6.0 molar, and I'm asked about milliliters. So I'm asked about volume. I like C for concentrated instead of stock. And then on the dilute side, I know that's what I'm after. I'm after 1.0 molar, and I want to be making 500 milliliters. The formula is going to be, well, it's usually M1V1 equals M2V2. I like to change it. Of course I do. MC VC equals MD VD. C for concentrated, D for dilute. I know that I have 6.0 molar, and I'm after the concentrated volume. And I know that has to be equal to 1.0 molar times 500 milliliters. Simple algebra now. Divide both sides by 6. The volume of concentrate that I need, 500 divided by 6. $83.33 milliliters. So 83 milliliters.